Good morning, good afternoon, good evening, everyone. Good day to everyone around the world, no matter what time it is for you. My name is Josh Epstein. I'm the Chief Marketing Officer here at Paris, and it's my pleasure to be moderating this panel discussion today. This is part of a series we call Pulling the Digital Thread, where we explore trending topics and technologies that are shaping digital engineering, digital manufacturing, product lifecycle management, and the whole digital enterprise, all from the perspective of a connected digital thread. So our goal is to bring together some speakers from around the world to exchange ideas and opinions and have some fun. We're streaming on a bit of a delay here to make sure we get good quality audio, so no live questions, but we do encourage you to participate on social, so particularly on LinkedIn. If you want to use the hashtag polling the digital thread in your posts. Please feel free to comment, to share your thoughts, ask questions, and the panelists and the team at Aris will be glad to help moderate the conversation and hopefully explore some of these ideas more deeply. So this discussion is recorded, will be available after the event. All right, so let's dig in. Today we're going to be exploring how AI and advanced simulation are really impacting this world of digital engineering. So I'm pleased to be joined by four leading thinkers on the subject. Welcome David Long from INCOSE, Tom Marnick from ANSYS, John Paul, JP Stein from McKinsey, and Matteo Nikolic from Aris. Welcome guys. All right, so just to start out, I'd like to ask each of our panelists to provide just a short introduction of yourselves, including your work on the topic and your thoughts about what's hot in this space. Tom, why don't we start with you?
Sure, thanks, Josh. I'm Tom Marnick. I'm at ANSYS headquarters in Pittsburgh, Pennsylvania. Been with ANSYS about 10 years, but I've been helping product development companies utilize technology to become more efficient for the past 40 years now. But I have to tell you up front, I'm not a simulation expert, and I'm not an AI expert, okay? But I do know a lot about product development, and I think I bring a unique perspective to how AI and simulation can work together to help product development companies be more productive.
Excellent. Great to have you here, Tom. David, why don't you go ahead?
Sure. Like Tom, I'll say I'm not an AI or simulation expert. My area of expertise is systems engineering. I've spent over 30 years in the field, founded and led two companies, Vitec and Blue Holon, in particular emphasis in the adoption of digital technologies, model-based, et cetera, which certainly sets the stage for AI and the inclusion of simulation. In parallel with that, I take volunteer leadership roles with INCOSE, the International Council on Systems Engineering.
Awesome. Great to have you here in the systems engineering perspective represented. JP, please go ahead.
Yeah, thank you. So hey everybody, JP Stein my name. I'm a McKinsey partner based out of Munich. I'm co-leader of our European digital engineering and digital twin service line, serving mostly clients in the automotive and assembly industries. And actually much of my work with clients is focused on planning, building and deploying digital twin solutions, including those that are based on artificial intelligence and machine learning, for example, leveraging our quantum black colleagues for this, and also working on the operating model. And prior to joining McKinsey, I worked at Siemens, and I'm a physicist by background, so very pleased to be here.
Excellent. Yeah, thanks for joining us. Matteo, please.
Hello, thank you, Josh. My name is Matteo Nikolic, and I'm from Aras. I'm a director of product management at Aras. So, since my university degree, basically, I was a simulation engineer and focusing on design optimization and robust design. And then I started this career in product management. And my previous company, we were focusing with my colleagues in building algorithm for design optimization and surrogate models. So I grow there my passion for this area. Now at Aras, I'm covering several parts of the platform, and including contributing to the AI introduction.
Excellent. Thanks, Matteo, for taking part in this. We're going to have a fun conversation today. I have just direct a few questions to each of you, but please, everyone, I encourage you to join in and ask questions and interact. So, Tom, I thought we could start with you. I mean, since we really are delving into really how simulation and AI are interacting. Let's start with you and your perspective, at ANSYS. So ANSYS, not a new company, founded in 1970, engineering simulation has been an established domain in product development for decades, and really kind of evolving. I think it's fair to say, I'm open to be challenged, but I think evolving adjacent to AI and AML based modeling relatively independently until some point in the last couple of years, or maybe the last several years. Could you maybe comment, Tom, on how AI is now shaping the future of simulation and really influencing the overall direction of digital engineering, PLM, and product development?
Sure. So, ANSYS has clearly been around, even longer than I have, believe it or not. And, they started as a physics-based simulation company, and really just in the mechanical space. And so really simulation that ANSYS has been performing for, 50 plus years now has really been focused on solving physics problems. And what ANSYS has been doing over the years to kind of round out the portfolio, you start off solving mechanical physics problems, and then you add fluid physics problems, and electronics physics problems, and so we've really been focused on being able to simulate anything that can happen in the real world through a very large portfolio of physics-based simulation solutions. Now, what's been happening, in the past decade or so is as AI starts to emerge and machine learning starts to emerge, it starts to become a possibility to get the same kind of results that you get from simulation without actually having to solve a physics problem. And so we have been exploring those things in the area of machine learning, very large databases of information about how the product actually performed in the real world, and being able to use that, much like, say, ChatGPT and other AI technologies kind of use large language models to be able to answer questions and write. ANSYS has been exploring using, large databases of actual product performance to get the kind of results you'd get from physics-based simulation. And as AI comes into the picture, it becomes even more interesting because AI can then make predictions and suggestions and other kinds of things that you're not necessarily getting, from simulation, in terms of just solving a physics problem and getting results of how that product is going to perform in the real world.
So maybe there's a couple things there. Maybe we can double click on a few of first how I guess modern AI techniques can perhaps be more, I don't know, is it fair to say computationally efficient than classic simulation, or is that the right way to look at it?
Yeah, I mean, I think so. AI can do things much faster. A neural network in an AI infrastructure is going to compute much more quickly. I think we've all experienced that if you've done any, dabbling with the AI technologies that are available today. You get instant responses. So the AI engine can perform much more quickly. Physics-based simulation is tedious. There's a lot of effort involved, right? You have to build a 3D model. You have to put a mesh on it, or depending on what kind of simulation you're doing, right? You have to do a lot of setup to prepare to run the simulation. And if it's a complex, say, fluids-based kind of a simulation, for example, it could take hours, sometimes days, even weeks to get results. And AI can do the same kinds of things much more quickly.
I think JP, you and I talked earlier about some of the work you've done in deep learning surrogates. I mean, could you share your thoughts on this topic in particular of kind of how AI techniques can perhaps I don't know, offload or could perhaps make better use of cycles in solving some of these difficult problems?
Yeah, absolutely happy to, right? And I fully agree with you, Tom, in terms of what you said. So AI is definitely able to make predictions much, much faster. And I think to give a bit like additional nuances to this, I mean, in the end, when you use AI or machine learning, it's about training and inference, right? So the inference, indeed, it's super fast. The inference meaning the predictions. However, then in the beginning, you of course need to have some training where you need the data that you were referring to, yeah, to make the AI model, so to speak, learn the physics that's behind that. And now actually coming to your question, Joe, specifically on the deep learning surrogates. So this is really a new and fascinating technology that actually allows partial replacement of classical simulation, hence the word surrogate in there. And why I say partial, I'll explain in a moment, right? But what you essentially do is you train the AI model based on the full data that is coming out of the simulation. And when I say full data, it means it includes the vector and scalar fields, for example, attached to a mesh, right? And then you let the AI, quote unquote, do its magic. And when I say the AI, it's a convolutional neural network in many cases. And there's really a number of benefits that you get out of this, right? So one is like, it's much, much faster. You can do many more simulation runs, and you can get towards the physical optimum, essentially, given a certain number of constraints that you are applying to a design, right? And maybe to bring this more to life and to give some numbers. So when you run such a deep learning surrogate, you get also as an output the vector and scalar fields as you would do with a normal simulation run, number one. Number two, you can achieve very high fidelity levels, so of 95 up till 99% measured in terms of R squared, right? And maybe what's really there in terms of the true power is when you combine this with a morpher, so you can cycle through many, many designs in a split of a second for one individual one, and then get really many more simulation runs, allowing you really to get to a really optimal design. So I think it's super powerful, super fascinating technology.
Oh, very fast. I'm going to ask JP afterwards. Maybe I think you had written some stuff. Maybe we can put in the chat just some link to some of the work, because I think that there are a lot of people listening that are going to want to reread that and kind of really listen to what you just said there.
Absolutely.
I think, Mateo, if I can turn to you, because I know that you got I think a lot of experience in kind of more algorithmic approaches to optimization. I think it'd be interesting just to differentiate, the differences, or how to think about the relationship between conventional optimization with some of these techniques that incorporate modern AI learning models and generative design. What are your thoughts on maybe just differentiate to the listeners what we're talking about?
Well, yeah, I make very simple. I can differentiate maybe on three different characteristics, like the exploration capability, the level of adaptability to the problem, and the complexity of the problem they can handle. So I would say that if you take conventional methods, they're focusing more on local optimization, on local, even if it's a global exploration, is fairly local. And while AI or machine learning models can explore a larger and more complex spaces and with predictive elements, right? And for example, also generative design can search the entire design space by generating different choices. So in terms of adaptability, I think that conventional methods can be, or like normal optimization can be less flexible and needs manual adjustments to new problems, and while learning problem can self-adapt. And in terms of complexity, of course, the more complex model and bigger model can handle more complex, nonlinear, multi-objective problems, and where conventional optimization is often limited. Now we have to say something about this, because this is on a very high level characteristic, and you say, okay, why don't we use the biggest model that we have? And now that we have a lot of very, very big models available from the scientific world and from the different companies, how do they apply to the optimization? Well, the more you enlarge the ability of the model to search a larger space, a complex problem, the less accuracy you might have. So I think that a good application is kind of having an AI can supervise also multi-models in order to be adaptive in the way that they search the space, especially for simulation. So it can search globally and then narrow down for more precision and more accuracy on a solution in order to identify and create a subspace or local surrogate models that can be used for further analysis, optimization, and for productivity. So that can be a usage of balancing the capability of different models together.
Gotcha. Okay, like I'm hanging on with like with barely here. So I want to bring us up a little. We got in really deep really quick, which is cool because I think that obviously there's a tremendous amount of technology here, and this is moving really fast. But David, when we first talked, you know, from a systems engineering level, we talked a little bit, a lot about the democratization of how AI can bring about the democratization of systems engineering and systems thinking and really help, mere mortals, kind of mere business people or everyday engineers, kind of leverage some of these concepts more proactively. Can you maybe talk about your thoughts there?
Sure. So, first off, systems engineering is based on the idea that the collective intelligence of many is greater than the singular intelligence of one, because you're working in complex problems that span multidisciplinary spaces, so no one person knows it all. So, what does AI bring to this? It brings an additional intelligence to that group, but actually, it brings multiple intelligences to those dialogues. So, if you're working in a multidisciplinary space, you can think about using large language models that are trained in specific domains to help augment the engineering expertise for various subject matter experts. You can start to play those together to look for interactions in very early days that perhaps we wouldn't have anticipated, because when you're bringing together those disciplines, you're trying to avoid the unintended consequences while getting the objectives that you're after. So that's at a large language model space. At a small language model space, you can think about starting to train these models with your corporate data to identify your design patterns, to identify your architectures, and start to do some of these generative design alternatives to try to live on the efficient frontier, all of which is a good co-technique alongside the engineer, which helps democratize it. Now, let's play simulation into that as well. And simulation can be played into two effects. One is actually back into the problem space definition, because as we start to explore very early solution concepts, we have the opportunity to play them back to the customer, to the operator, to the user to say, did we hear you correct? Because more often we solve the wrong problem than get the right answer to, or get the wrong answer to the right problem. So we can do very early validation back to the customer using these simulation techniques, and then pair it with AI for continuous evolution downstream. All of that is, it's really founded on this idea of it is one more set of intelligences that we can bring to co-engineer and assist the experience.
That's fascinating. I mean, how stepping back, how do you think this changes the role of an engineer? Kind of what if we look ahead, 5 years, like how is this going to change the role of a design engineer and kind of the skill sets that organizations need to be hiring for?
It's a tough question, Josh, because I think if we forecast today's seasoned engineers, then you can see how AI can work as a very effective partner. It can handle a lot of the perspiration of the role and free the engineers for a little more creative design, while at the same time leveraging the collective insight that they've brought over the years to spot bias and other issues, delusions in the AI that they can then counteract. So I can see engineers 5 years from now really focusing more on the innovation side of it and allowing AI to handle the perspiration, the bookkeeping, the consistency, all those aspects of design, the data exchange, etc., while also proposing new alternatives. The biggest challenge, though, in the field is, and what happens when we lose our seasoned engineers? How do we develop the next generation of engineers to actually have that same skill set and work compatibly with AI, trusting it to the right level and not over trusting it?
No, I like that. Tom, I'm curious on the subject of democratizing systems engineering. Obviously, I mean, ANSYS made its name for creating powerful simulation software used by, PhDs, right? And so, and I know that you spend a lot of time thinking about simulation data management. I'm curious, maybe start with you, Tom, but the broader team, like that, the key to managing all of this data? I mean, simulation data management, but I'm thinking AI data management. How do you actually kind of make these models and the outputs of these models accessible? And how do you think about data management, data governance, and those subjects?
Sure. So David, brought up a really interesting point, based on your question, Josh, which is, what are engineers going to be like? What are they going to be doing in the future? And one of the things that AI really helps with is it gives you the ability to explore possibilities that you wouldn't have time to explore under ordinary circumstances. One of the things about simulation, you know, you can solve a physics problem with simulation, kind of as it's been traditionally operating today. And a lot of times you need a PhD, not only to set up the problem, but then also to even interpret and understand the results. Um, so, that's pretty challenging. And you're investing all this time in setting up a problem and running a simulation, and you're running a simulation for a very specific set of circumstances, a very specific set of conditions. And the challenge is, what simulation should I be running, right? To really make a good engineering decision, a good product development decision, what simulations should I be running in order to get the information I need to do that? And that's where AI can have a major role in giving me the ability to, infer things, predict things that I hadn't even thought of or hadn't maybe considered, and run through a much larger problem set. So that's one thing.
Hmm.
Now, the key to making that work alongside, based on your question about managing the data, okay, AI is only as smart as the information that it's been given to learn on. So if you give it a bunch of bad information, a bunch of bad data, it's going to make a bunch of bad predictions, and a bunch of bad inferences. So it's the age-old garbage in, garbage out issue, right?
Hmm.
And not to get product specific or promote ANSYS products directly, we have a product called SimAI that looks at past simulation results. You feed it simulation results from the past, and it runs, makes predictions and gives you ideas and optimizes potential designs and things like that. It gives you feedback based on those simulation results. Now, if you're feeding it, you know, either garbage simulation results or simulation results that are out of context or simulation results that don't really apply to the kind of problem that you're trying to solve, they're just not, kind of the best kinds of results you could be giving it. You're not going to get the best recommendations from the AI engine,
Hmm.
right? You're not going to get the best ideas. So having a systematic way of organizing the data, putting context around the data, indexing that data, making that data understandable to the AI system that is going to learn on that data, is really critical. So I think a lot of what engineers are going to be doing in the future is making sure that the models that feed AI are organized and accurate and relevant. And then I think they're also going to be doing a lot more of, they're going to be using AIs. I think the key here, another key point to remember, right? AI is a tool that engineers are going to use to gather more information that they can internalize and then use that to make better decisions. And so it's all, it's all connected, right?
Yeah.
I've got to teach the AI with useful stuff, as best I can, and then I've got to interpret what the AI gives me,
Hmm.
using my my engineering knowledge.
Yeah. No, it's okay. No, cool. We talked about data. We've talked about some cool math and some cool applications. Let's maybe delve into the real world. JP, I know you've done some research on different industries, looking at industries that have looking at the relative progress each has made around leveraging engineering simulation. You want to just share your insights and maybe share particularly examples of those industries that are most advanced and those that are maybe just getting started?
Absolutely, happy to. Right. So indeed, we did extensive research on this jointly with NAFEMS, where we ran a survey actually last year across industries and across both users of simulation technologies and providers of these tools. Yeah, it was in total like almost 200 participants in this survey. And we looked at both, let me call it more classical engineering simulation tools and AI and ML based tools. And I think there were really a number of very interesting insights that we derived from that, right? And number one, actually, the first one that I would like to highlight is that actually we looked at drivers of the use of engineering simulation in the past and now in the future. And what we saw actually, there was a shift. Yeah. So in the past, actually improving product performance was number one. Now it's faster time to market. Yeah. So this has actually changed. Before that, faster time to market was, I think, number four. Now this has shifted. And I think there's clearly a pressure also in the industry, specifically those that I'm serving around automotive, to achieve faster time to markets, to be more innovative, and to also match the cycles that, for example, we know from other appliances such as cell phones, where we have like really, or smartphones, where we have really fast introduction of new tools and technologies there, right? Now, if we look at what is now specifically more at AI and ML therein actually, we notice that actually in terms of the adoption, like most industries are still in the, let's say, starting with adopting AI and ML based techniques, right? So overall, we had only like 5% of respondents saying that AI and ML are used at scale, right? Whereas a majority, roughly 60%, are using proof of concepts. And then actually another like one third of the respondents said it's not being used at all, right? Whereas for classical simulation, I mean, more than half said that it's used at high maturity and at scale. So there's clearly a huge difference, meaning there's still a very large learning curve, right, to be done. And now next to your specific question, how are different industries using that, right? So in the automotive industries, 76% of respondents actually said that they are already using AI and ML for their virtual engineering tools. Whereas in other industries, such as medical devices and machinery and fabricated metals, is more on the order of like 50% of the responses that we got. And I think this is very much linked then as well to the dynamics of the industry, where, for example, in automotive, there's lots of pressure, as said, to be fast, to move to a quicker time to market, to improve the design even further, given all the pressures on cost and also the competitive dynamics that we see.
That's it, Chad. I'm really curious, David, how this maps to your understanding of the adoption or really embrace of formalized MBSE or in systems engineering in general. Does that correlate? I mean, I think there's probably a lot of similarities in the drivers of why people are embracing it. I think time to market being one of them. But yeah, well, what are your thoughts?
Yeah, absolutely, Josh. So initially, MBSE was another tool to deal with complexity. But as we deal with the competitive nature, whether it is in the defense domain where you're talking about peer adversaries, if you're talking in the commercial domain, I need to be inside the learning and innovation loop of my competitor. It is actually far more now about time to market and shortening that time to market with better design, but then through combined AI and simulation techniques, continuous verification to shorten that cycle time over and over and over again. It's velocity, and we're seeing some of the leaders, as JP said, is really automotive. They have tremendous market pressures to do so and to innovate on those fronts.
I'm curious, Matteo and Tom, just thinking about this optimization of product design versus accelerating time to market. What are your perspectives on what are you seeing out there? Is one prioritized over the other, or maybe just your perspective on how teams prioritize one or the other?
Well, it's Let me think about.
It's a
All
tough
things
one.
are very important. I mean, the idea of optimizing and it all goes down to the to supporting the decision making process with and assisting it with more data and more information in order to have a more conscious decision making. So in the design process, so it means when applied the AI or machine learning, all these techniques, it goes down to simulation, so help the user, the simulation engineer to generate more data and explore more solution potentially, and this feed more data for the decision making process. But then all this data needs to put into a context really. So it needs to contain not only the single simulation artifact or information about the performance of the product, but it's everything in the context of where this was generated during the design process. So you can go and optimize for the usage of resources for simulation. For example, you can use surrogate models in order to reduce the number. You first use simulation to reduce the number of physical prototyping. You then use surrogate model to reduce the number of actual simulation activities and computational resources. And then you use that to feed more informed decision-making process in the design phase. Everything goes into the context. So the idea of the digital thread and connecting all the information that goes together about the simulation activities is very important to help the company that are designing product and that can rely on this technology.
Yeah.
I kind of feel like it always seems to me that everybody wants everything all at once, so choosing between faster time to market and optimizing designs, they want to do both, right? And as long as I've been in this business, right, everything always boils down. All technology has obviously come a long way in the time that I've been in the industry, and there's always innovation happening on the technology perspective. But the technologies usually get applied to help customers do things better, faster, and cheaper.
Mm.
And that means better product, higher quality product, which requires more optimized designs, exploring more design possibilities to choose the best one. Engineers being more productive, everybody being more productive, and getting products, high quality products out the door faster.
No, absolutely. And I guess I'd like to maybe as we get towards our time here, maybe wrap it up by getting back to the human factor a little bit. Something David, you mentioned, I think, in the hands of a seasoned engineer, right? That extremely powerful tool set. Curious on perspectives on how do you get teams to embrace this? How do you get individuals to nurture an understanding of how to develop this? Maybe JP, starting with you. I mean, obviously, people can hire McKinsey, and you can come in and kind of coach a team on how to adopt, new approaches to solving complex problems. But how do you actually get that kind of momentum going in an individual team, and then ensure that you're nurturing kind of the new generation of engineers that can still think critically and can still develop that kind of gut feel that also goes into spending money, spending time, and deploying resources.
Absolutely. And this is a question that honestly we actually get asked super often. So in very many situations, actually, our clients come to us and say, look, actually from a technology perspective, we feel quite confident. Yeah. But in terms of how to scale this, how to get away from just having a number of POCs, proof of concepts running, but really scale this across the enterprise and then capture the benefits from that. This is really something we are struggling with and where we would absolutely appreciate some help, right? And here I think there is a number of elements and initiatives that you should do, right? Number one, and just going through now a couple of those, right? But number one, I think this needs to be really something communicated from the top that this is wanted and needed. Yeah. And to achieve this communication from the top, also top management in the end needs to understand what are the benefits, what can be achieved. Yeah, and that it also requires some change from the people to get there. And actually, managers also need to learn here and there a new language, yeah, especially when it comes to AI and ML. So there's to some extent need to also be trained. I think this is one element. Another element is to really engage the people. Yeah, and here I think it's clear to important to differentiate between different let's say, types of people. So you have, let's say, more seasoned people that have used the, let's say, classical tools for a very, very long time, right? And the people who are, let's say, maybe more new, have more experiences from university, other players, and so on. And for these, you need to have a very tailored approach to drive adoption in the end. What also has shown as super valuable is to say, how can you create an exchange between these individual people who are then having a different learning curve, having different questions, maybe having different objections, right? And really creating these forums where they can exchange best practices, where they can exchange what worked, what didn't work, what were some pitfalls, is actually super important, right? And then the other one is to create a bit of a, let's say, even competitive spirit, right? Which is to say, okay, where do we stand with our adoption? Who is already using it? Maybe there are some lighthouses where there's really cool benefits being extracted that you can share with other people, and where people say, great, I also want to do this. I didn't know this was possible. So this is just, let's say, roughly 3-4 things and specific initiatives that you can do and drive. That's much more. And super valuable, because in the end, this is about really revolutionizing the way you do product development in the longer term. And you need to take these steps to be successful.
No,
Josh,
yeah.
building on what JP said, there's a very important message that he buried in the middle that I don't want people to miss. And this is similar to what we've seen in model-based systems engineering and digital engineering. We always talk about how important it is to have top management to provide that direction and that top cover. And we talk about how important it is to have the frontline workers adopt it. The layer that JP touched on, and we can't forget, is middle management. Because middle management is where change goes to die in an organization. And for good reason, middle managers are empowered to keep the existing processes running the right way. If we have change, and if we want to see innovation and adoption in these areas, we need to make it clear to middle management how this helps them advance their objectives, their organization's objectives, et cetera. Because that's actually the gear, the wheel that enables the pieces around it.
Thank you, David.
I would go a step farther in that, because I think that around this AI right now, there is a big hype and there is a lot of interest in companies in big complex problem and a huge return of investment that is potentially not achievable in the short term, right? And when apply this, there are a lot of investigation today on how you can apply on big topic, on big change in the process of the company, but they don't always take into consideration what will really help the end user or the engineer in the team, and doing the day-by-day task. So we said that one of the things that the AI can do is support reducing the repetitive tasks and focus more on innovation and other things. So I think that in order to help that and help the final user, we need to start small, right? And think about the small use cases that really enhance the work, the day-by-day work of the engineers, and then grow in the company towards bigger scenario. Because otherwise, if you start from the big picture, then you may have problem with the adoption. You may have problem with the reality, right? You assume that you have all the data, while it's not the case. For example, you assume you have connected system, while it's not always the case at first, and all these things that are the reality of the engineer.
No, fascinating. Tom, I'm struck that, a lot of these things, these same scenarios must have been, tackled in parallel and from the simulation world. And I like what you said before about the need for connected information and making sure that, that the organization can understand what simulations or what models or other digital artifacts are available in the decision-making process. I'm just maybe back to the whole theme of data management and ensuring that, resources are findable, that you can apply an AI, or advanced search or any type of kind of decision support tool to find that kind of data. But I'm curious your perspective on, how ANSYS in the simulation world evolved to solve this problem.
Yeah, so I think this applies, not just in the AI space, but across all of product development. everybody's using a bunch of different tools and technologies to accomplish various aspects of engineering, the engineering that has to happen to design and manufacture a product and service it once it's in the field. And so there's really a need for a platform that helps manage all of the information that gets created by all of these tools and organize it, right? And maintain this digital thread. Because all of this information that's being generated as people go about the business of engineering is digital, and it's all connected in some way, right? I can't do a simulation without a CAD model in most cases. So somebody did a design, generated a CAD model. I take that, I modify that CAD model to make it an input for a simulation I'm about to run. So I'm basically creating this, trail of digital information. And if we don't have a mechanism to tie that thread together, to keep track of it because it's constantly changing, everybody's doing different things. And the first time you do something is never the right, you don't get the right answer the first time, right? You're always improving it. So as this stuff changes, it's very easy to get out of sync. So you need a system, you need data management, you need a platform that helps people not only execute the tools and technologies, but also helps them keep track of everything and tie it all together and make sense of it all. And that's where, simulation process and data management comes into play.
Yep. Yeah.
May
It's
I
all
add
about the
to
data.
this?
Yeah, please.
Just very briefly, right? So, there's also an article available on this, but we built some kind of classification logic on digital twins. And indeed, the foundational level is really to make sure that exactly these data management, data foundations are in place properly. So this is absolutely the prerequisite to do anything on top, right? And then the next levels are around prediction, which, for example, you use simulation for. And then the level even above that would be what we call prescription. So really, in an automated way, getting to the best outcome using, for example, AI, ML techniques in a closed loop, closed circle to get to the optimal design, optimal outcome for a system in the end, right? But again, re-emphasizing the data management is absolutely key to get this to work, and to do any kind of training, for example, for AI and ML algorithms.
Absolutely. We always, in the analytics world, we talk about from descriptive to predictive to prescriptive, right? And I think that lays out the nice life cycle of applying data and advanced modeling techniques. Cool. Maybe I'll just end with what are you most excited about when you look at this space, whether it can be specifically an AI and simulation or, just your own personal pet project that you have with applying AI to your everyday job. I'm curious, David. What are you most excited about?
So I'm most excited at watching these technologies come together. We're in this age of computational power. So we talk digital engineering, digital twin, digital thread, model-based everything, AI, et cetera. As Tom and JP just noted, it's the data layer that powers it all. If we will bring that together with the experiences of the engineers, I think we can transform the way we do engineering from an old siloed life cycle phased approach to delivery of continuous value for the business. We're watching the evolution, the transformation of engineering, and we're living through it.
Awesome. Matteo, Tom, JP, thoughts?
Well, I'm really thrilled what excites me is see the interaction, how our interaction with the technology is shifting, and how we are. So beside the technology itself of solving complex problem and looking at the system level design or digital twin or real-time simulation potentially and feeding the data, it's really, and this will evolve and will continue with our capability. It's how we are evolving our interaction with this technology and how even I think about engineers, we talk about that, but also if you have experience playing with the chatbot, basically as an engineer, you usually are a problem solver, right? Now we need to shift into being problem framers to the AI. We need to be able to define the problem and then evaluate. We need to shift from being kind of analysts to being be able to interpret and validate the result that we are getting and we see. to be able to define tests and prototype and simulate in order to verify. So this shift is shift also the entire interaction with the technology, with any type of application, with AROS Innovator, with for PLM, with an SPDM tool, or with a simulation application. But I can say also with our own smartphone and our normal search in internet, right? And this is very exciting.
No, for sure.
I'm excited to see what we're going to build with these capabilities. You know, if I think back to the technological progress that I've seen just in my lifetime and the way that it's accelerated in the past, 10, 15 years, amazing stuff has been accomplished, amazing products have been built, and what AI brings to the table in terms of unlocking a whole new realm of potential possibility for innovation. I just can't wait to see what's going to come of it.
Yeah, me too. JP, last word.
So actually, for me, it's two things. Number one, it's actually using simulation, digitalization, AI, ML actually for the good of humanity, if I even may say so, right? And this sounds very huge, but let me make this a bit more concrete. So using AI simulation, for example, for the topics around sustainability. So for example, designing an EV that consumes less energy. I don't know, you're designing a washing machine that needs less water. Yeah. Things like that. I think there's like a huge number of possibilities when you think about really having this power to analyze designs almost instantly using AI and ML. I think that's super fascinating, and I think it's very much underutilized. There's so many more opportunities to that. Yeah. And then second, it's actually, and this is maybe a bit more the nerdy side of me speaking, right? I mean, what about the future when we have these tools used everywhere at scale? What's the vision out there, right? What is the equivalent of a large language model such as ChatGPT now for the simulation area? Is there something where we can ask the tool then any simulation question and it will provide us the answer, the physics-based answer, right? A universal tool, so to speak, that doesn't need to be trained anymore. I think that's a super cool vision. Or second, within that vision, as we talked about an engineer, right? I mean, do we have a fully connected tool chain where we scribble something or just voice a few ideas, it's automatically transferred into CAD, then automatically broken down into individual components, then these components are simulated, in the end brought together back into a car that is already optimized from a design perspective and from a physics perspective. And this is probably a bit further out in the future, but super fascinating, I think. Definitely something that is worth working on and driving forward.
Absolutely, well said, and certainly making the world a better place is definitely the mission of all of us. So I think that's a good place to wrap. We covered a lot of ground here. I'm definitely going to ask everyone maybe to share some of the pieces that you're reading. JP, I've loved some of the articles I've read that you've written. I'll share those. But this is a great conversation. Please let's keep it going on LinkedIn. With that, I'd like to thank everyone for taking the time to listen. Thanks, panelists. This was super fun. I know I feel smarter. So thanks for your time. Bye all.
Thank you. Bye.
Thanks, everybody.